Jupiter is not what you think. You were probably told Jupiter is just a giant ball of gas. That version is tidy and easy to remember, yet it does not match what we now know. Beneath those striped clouds lies a world of liquid hydrogen, flowing metal, violent impacts, and a core that refuses to behave in a simple way. Most of us first met Jupiter in a classroom diagram. It appeared as a round planet wrapped in bands labeled gas giant, hydrogen, helium, no surface, no solid ground. That picture settled in early and stayed there. When the first close photographs arrived, they seemed to confirm it. In 1974, Pioneer 11 sent back detailed images of cloud tops. 5 years later, Voyager 1 recorded moving views of storms turning across its face. The Great Red Spot rotated slowly, immense and steady from afar, though nothing about it was gentle. Those images looked like weather on a vast scale. They did not suggest oceans or metal beneath. The difficulty was not what we saw, but what we concluded from it. Clouds reveal little about what lies below. A distant observer studying Earth from orbit would see white swirls and blue surfaces without knowing about forests, deserts, tectonic plates, or a molten interior thousands of kilometers deep. Early views of Jupiter showed atmosphere, not structure. Its size deepened the misunderstanding. Jupiter outweighs all the other planets combined. Roughly 1,000 Earths could fit inside it. If Earth were a grape in your hand, Jupiter would fill the space like a basketball. That scale shapes the entire solar system. Its gravity redirects comets and gathers asteroids. The inner planets formed in part because Jupiter absorbed enormous amounts of material early in the Sun's history. It never ignited nuclear fusion, yet in many respects it behaves like a star that did not quite cross the threshold. Such dominance raises a natural question about origin. For years, the prevailing explanation appeared adequate. A young sun formed within a rotating disk of gas and dust. Tiny grains joined to form rocks. Rocks collided and grew into larger bodies. One of those growing masses reached a size where gravity allowed it to capture vast quantities of hydrogen and helium. Over time, that object expanded into Jupiter. Under this model, a compact core of rock and metal would sit at the center, surrounded by thick gaseous layers. Another possibility remained under discussion. A large clump of gas might have collapsed under its own weight, forming a planet without a sharply defined rocky seed. That process resembles star formation on a smaller scale. If that were true, Jupiter would consist of layered material without a distinct core. Classrooms favored the first model, largely because direct evidence was limited. No spacecraft had probed deeply enough to resolve the issue. A rare event shifted the conversation. In July 1995, the comet Shoemaker-Levy 9 fell into Jupiter after being torn apart by its gravity. More than 20 fragments were struck over 6 days. The largest impact released energy equal to hundreds of millions of atomic bombs. Observers on Earth faced a complication. Since the collisions occurred on the far side of the planet, the event might have passed unseen. Fortune intervened. The Galileo spacecraft was approaching Jupiter at that moment. As fragments entered the atmosphere, plumes of hot material rose thousands of kilometers above the cloud tops. Dark scars, each large enough to swallow Earth, marked the impact sites. When Jupiter rotated, the Hubble Space Telescope recorded the aftermath. More importantly, debris from beneath the cloud layers had been lifted upward. Galileo moved through that disturbed region and gathered data from material previously hidden from view. Among its findings was water in unexpected amounts. That observation challenged earlier assumptions. If Jupiter were a simple gas sphere wrapped around a tidy core, the distribution of water should have followed a different pattern. Instead, the data pointed toward complex mixing inside the planet. These results led to a new mission designed to examine the internal structure directly. The spacecraft Juno, launched in 2011 and placed into orbit in 2016, carried instruments capable of measuring gravity, magnetic fields, and variations in mass deep within the planet. Rather than relying on photographs, Juno interpreted the interior through subtle changes in its own motion as it circled Jupiter. The results forced a revision of the old description. Jupiter does possess a visible cloud deck, yet that layer averages only about 50 kilometers in thickness, which is thin relative to the planet's size. Temperatures in the upper atmosphere fall below -100 degrees Celsius. Ammonia mixes with water ice and allows liquid droplets to exist at higher altitudes than expected. Lightning flashes across storm systems that extend far downward. Hail, composed composed of ammonia and water, forms, melts, evaporates, and rises again in repeating cycles. The Great Red Spot reaches hundreds of kilometers into this region and absorbs intense sunlight, which drives chemical reactions that produce its color. Impressive as these storms appear, they rest upon something far denser. As depth increases, pressure rises steadily and heat follows. At roughly 1,000 kilometers below the clouds, hydrogen gas no longer behaves as a gas. The weight of material above compresses it into liquid hydrogen, even though temperatures exceed 1,000 degrees Celsius. This liquid region extends downward for about 20,000 kilometers, forming a global ocean far deeper than any on Earth. At that point, describing Jupiter as primarily gaseous becomes inaccurate. Much of its volume exists in liquid form. Conditions intensify further inward. Pressures climb to millions of times those at Earth's surface, and temperatures approach 10,000 degrees Celsius. Under such extremes, hydrogen undergoes another transformation. Electrons move freely between atoms, allowing the fluid to conduct electricity. This state is known as metallic hydrogen. The layer spans tens of thousands of kilometers. As Jupiter rotates, this electrically conducting liquid moves with it, generating an immense magnetic field. That field traps charged particles and creates powerful radiation belts. Spacecraft traveling near the planet must be shielded carefully to prevent damage to sensitive equipment. At the center lies a structure once thought to be simple. Earlier models pictured a small, compact sphere of rock and metal. Juno's gravity measurements suggest something more complex. Instead of a sharply defined boundary, heavy elements appear to blend gradually into the surrounding metallic hydrogen. The result is often described as a fuzzy core, a dense region where rock, metal, and fluid mix over a broad area rather than forming a clear edge. Such mixing requires explanation. One proposal involves a massive early collision with a large protoplanet. An impact of that scale could have stirred the interior and blurred boundaries between layers. Computer simulations show that such collisions can create extended cores, yet many models predict that the interior should settle over time into a more compact form. Jupiter's core remains extended, and the evidence does not provide a definitive account of how it formed. The implications reach beyond Jupiter alone. The planet gathered enormous mass early in the solar system's history. Its gravity influenced the paths of smaller bodies and helped shape the layout of planetary orbits. The position of the asteroid belt and the distribution of material that later formed Earth may reflect Jupiter's presence. Observations of distant stars reveal many giant planets orbiting close to their suns. Astronomers use Jupiter as a reference point when interpreting those systems, since its internal structure and growth provide valuable comparisons. Jupiter occupies an intermediate place in cosmic classification. It is not a star, yet it contains processes that resemble those within stars. It is not a small, rocky planet, yet it contains heavy elements and a layered interior. The study of this world tests physics under conditions difficult to reproduce in laboratories on Earth. A concise summary clarifies the current understanding. Jupiter carries a relatively thin outer layer of ammonia and water clouds. Beneath that lies a deep ocean of liquid hydrogen. Below that ocean rests an even thicker region of metallic hydrogen that conducts electricity and drives a powerful magnetic field. At the center sits an extended core where rock and metal blend gradually into the surrounding fluid. The layers exist, yet their boundaries are not sharply defined. This portrait replaces the earlier image of a simple gas sphere. Jupiter is largely liquid in bulk and partly metallic in behavior. Each mission refines the model, yet unanswered questions remain. The broader lesson concerns the nature of scientific inquiry. Descriptions once treated as settled can change when new measurements provide clearer evidence. Jupiter demonstrates that understanding grows through observation, revision, and continued investigation. A planet once introduced as a straightforward gas giant now appears as a layered world of compressed hydrogen, metallic interiors, and an unresolved origin. That shift did not occur suddenly. It developed through decades of patient research, fortunate events such as a comet impact, and deliberate missions designed to examine the unseen. Continued exploration promises further insight, and each discovery brings us closer to understanding not only Jupiter, but the processes that shape planetary systems throughout the universe.